Boy, somebody knows their Spanish over there.
Well, I thought that's what it said, but I'm confused what calculus has to do with a house.
Related rates, also known as El Gato de las Nueve Vidas, the cat with 9 lives, which is this cat that's talking right now.
What?
Is there a joke I'm supposed to be understanding?
You'll learn,
Okay.
as I am the cat with 9 lives. Anybody recognize this house? Down by Flint Field, just across the street? It's Max Bruns' house. Max and Allison, you know.
Oh, okay,
Okay, yeah, okay. I painted that house. Kind of a big house. See how big it is? Well, Mr. Bierschbach set up some scaffolding like this. Okay, then he put his ladder up like this. And Mr. Bierschbach was here painting, reaching up, painting up here, when all of a sudden the scaffolding tipped away from the house. Ladder fall down. Mr. Bierschbach fall down, go boom. Okay.
What? When was this?
Oh, this was several years ago.
Are you okay?
Oh, yeah.
Were you okay?
Well, basically, yeah, I didn't break anything. I kept painting. So then I fall down, go boom, you know. There's a lady sitting at one of those picnic tables at the park where the Flint Field is. She was reading a book. She looked up after all the commotion because obviously it made big bang. She looked up. I kind of looked at her. She was like, put her head back down in the book. Did not ask if I was all right or anything. I fell onto the roof. I fell onto the roof of the porch. I fell onto the porch roof, not all the way down to the. I would be dead if I was. Okay, so how does this relate to what we're talking about today? It doesn't. But if you're on a ladder, and let's say this is a slippery surface, and the ladder starts going this way. How fast are you going down this way? That is related rates. Oh. What? Oh, something to do with that, yeah. No, I'm sorry, but this is what we're doing. So, okay. Thanks for letting me know. So, you know, that's not the only house where I had ladders go down on. Like there was a house that, you know, well, it wasn't on a house. There was like a tree where it had some branches coming out. It wasn't that full of a tree, but it had some branches coming out. So, and then there's this like weird branch that came way out and it made the tree look ugly. So I put my ladder up on the tree like this. And I was chainsawing right here to get rid of the ugly part. Well, Mr. Bierschbach, just as he did a poor job in his physics here, because the physics of how I set this up, I set the scaffolding too high, which allowed it to tip because it was too far away from the house and that, you know. So again, physics here, Mr. Bierschbach wasn't thinking when he sawed. Because if you saw off a tree limb here, what do you think will happen with this part of the tree limb? Well, it got rid of a bunch of weight when I sawed this off. When it gets rid of a bunch of weight, for every force, there's an equal and opposite force type of thing. This went up. Ladder was only this high. With a chainsaw running in my hand. Ladder fell down and go boom. Mr. Bierschbach, again, was alive. And I went and kept working on the tree about 15 minutes later because I was rolling on the ground. I was I hit really hard that time.
At least you didn't hit the chainsaw.
No, chainsaw, you know, Yeah, I kept it away. I kept it in my hand the whole way down, but kept it away from my body. It was amazing. Yeah, okay. That was, I think, before I ever did the Bruns house of falling down, go boom. And then there was one other incident I had. It was on a house, which was, okay, imagine if there's a porch out this way as well. Okay. And so I had my ladder up here painting when my ladder fell down and I was hanging on to the eaves trough, but like the porch ceiling went up like this. So I had to go hand over hand to get to where I could drop onto the porch and not die, type of thing. So those are my three major ladder incidents of me painting where, I could have died, but, I found a way to live. And I still paint to this day. Your mom asked me to, but Gores is doing it, so. Okay, so how does this work with related rates? Well, related rates are this. Okay. Here's a ladder that somebody stupidly put up against their house. They're putting up Christmas decorations, they're hanging lights, and it's a little icy on the ground. And you should not put a ladder on the ice. But, people as stupid as Mr. Bierschbach do crazy things. No, this is not me. I never did this. I'm not quite that stupid. Okay. Now, if the ladder is 25 feet tall, okay, and it starts slipping away from the house at a rate of 4 feet per second, if Mr. Bierschbach is at the very top of the ladder, how fast is Mr. Bierschbach falling down this way? And this occurs when the ladder is, let's say, 15 feet away from the bottom of the wall. Okay? So how fast is Mr. Bierschbach falling at when this is 15 feet away from the wall? Okay? Well, what do we have right here? A right triangle. Thanks for just not saying a triangle, but it's a right triangle. Okay? So if this is 25 feet and this is 15 feet, what's this? We do the Pythagorean theorem. C squared equals A squared plus B squared. So 25 squared equals A squared plus 15 squared, right? So 625 equals A squared plus 225. Subtract 400 equals A squared. So A equals 20, right? So we know all the lengths, okay? Now, this involves a right triangle the whole time. This involves the movement of a right triangle, okay? So the distance here, all the distances are involve the x-coordinate and the y-coordinate. So c squared equals c squared equals, let's do it the other way. A squared plus b squared equals c squared, where x, we have an x distance and a y distance, but the ladder is always, because these are changing. This 20 changes, this 15 changes. As it slides out, this slides down, okay? But the 25 will always be the same the whole time. So equals 25 squared. So since things are changing, what we do is they change over time, okay? We change with respect to time. Okay? So if we change with respect to time, we're adding a third variable into here. Okay? Not just x or y, but we're adding time into here. So what's the first derivative of 2x squared? So it's going to be 2x, and then we're going to say it's dx dt with respect to time. The change in the x amount with respect to time. And then this would be 2y dy dt, the change in the y variable with respect to time, equals, and the first derivative of 25 squared is just 0. Okay? So this is my dy dt. How fast am I going down? This is dx dt. How fast am I going in the x direction? Okay? So I know my x value is 15. I know my y value is 20. So 2 times 15 times 4, because I'm moving at 4 feet per second, dx dt, plus 2 times 20 times we don't know, dy dt, is equal to 0. So now this will tell us how fast I'm falling. What's 2 times 15 times 4? 120 plus 40 dy dt equals 0. So 40 dy dt equals negative 120. So dy dt equals negative 3. So I'm falling at negative 3 feet per second at that point. Okay? So when the ladder is situated like this, I'm only going down at 3 feet per second, which is, fairly fast, but not super fast. Now, as the ladder gets further away this way, I'll actually fall a little faster this way. Okay? So let's say that it's still going at 4 feet per second, but now the distance that the ladder is at the bottom is now, well, just to make it easy, let's make this 20. So this is 15. Okay? So it's 5 feet further this way and 5 feet further this way. Okay? If we do that same problem, you'll see that this changes a little bit. Okay? So this doesn't change. 2x dx dt plus 2y dy dt equals 0. So if x is now 20 and it's moving at 4 feet per second out, if y is 15 and it's moving dy dt out, 2 times 20 times 4, 2 times 20 is 40 times 4 is 160, and this is 30. So if I move the 160 over, and if I divide by 30, I get like 5.33 or negative 5.33 feet per second. So as this gets further out, the speed that the person is falling increases. Okay? That's related rates. Okay? That's the gist of related rates. Now, there's a lot of work to do today of various types of problems that they show you. Okay? So, the height of a rectangle is increasing at 11 centimeters per day. So, we draw a rectangle. The height is increasing, so dh dt is increasing at 11 centimeters per day. Okay? And the width is decreasing at 9 centimeters per day. So dw dt, the width is changing at negative 9 centimeters per day. At a certain instance, the height is 3, so h equals 3, and the width equals 8. W equals 8. What's the rate of the change of the area at that instant? Okay? Now, it says, what is the width measured in? We're just looking at the units that were measured in. What's the width at that time measured in? Just plain simple centimeters. That's what this means, is what's the width at that time equals 0. Okay, let's jump down to the height. What's the height at that time? That's also in centimeters. What's the area measured in at that time? or no, what's the area measured in, or what's the change of the area? That's what this means. What is the change of the area as time is changing? Centimeters squared per day. So the area would be centimeters squared. And if we had like the, what is dH dt, dH dt would be centimeters per day. Okay, see how that works? That's related rates as far as the units go. So now we're looking at this one, the radius of the base of a cylinder. So here's the cylinder. So the radius is getting smaller at 9 millimeters per hour. So that's dr dt. Okay, or this, the first derivative of r. Okay. The height is increasing, so dH dt is increasing at a positive 2 millimeters per hour. At a certain instant, the radius is 8 millimeters and the height is 3 millimeters. What is the rate of change of the surface area at that instant? Okay. Well, the surface area at that instant is what? Is it going to be 3, 8, 2, 9, or some other number? Some other number. Because the surface area, we have to use the surface area formula, which will not be, the surface area of a cylinder is over here. And you'll actually use these today a little bit. The surface area of a cylinder is 2 pi r squared plus 2 pi r8. Not any of those numbers down. Okay? What is r prime? R prime is the change of the radius. How is the r radius changing? -9. So that is -9. H sub t is a change of the height. How is that changing? +2. Okay? So you'll be given questions like this to kind of start to decipher what goes with what. Okay? Then we'll look at calculating a problem. A person stands at a distance of 18 meters east, intersection, east of an intersection, and watches a car driving away from the intersection. So the car is going this direction at 3 meters per second. 3 meters per second. So that's your dy dt is 3 meters per second. Okay? The function y gives the car's distance in meters north of the intersection at the time. At a certain instant, time equals 0, t sub 0, the angle theta between the line of sight and the person is to the intersection is 0.7 radians. What's the rate of change of the angle at that instant? Okay, so if we're dealing with angles, okay, if we're dealing with angles, there we go. Would it involve the tangent, that, a triangle with 180 degrees, or the Pythagorean theorem? Which one do you think would be most likely to deal with an angle changing? This is the area of a triangle. This is how many degrees are in the angles of a triangle. This is the lengths of the sides of the triangle. And this is a tangent. Which one do you think it would be of the changing angle? Nobody wants to offer a guess? Tangent.
I've done that about 15 times.
Well, you didn't really voice it very loud.
I think everybody else heard me.
Well, I didn't hear you. Yes, exactly. It is the tangent. Because the tangent is the length of the opposite side over the length of the adjacent side. And if it is changing, that angle will change. And yeah, you use the tangent in that case. Okay? The radius of a sphere is decreasing at 1 meter per hour. At a certain instant, the radius is 4. What is the rate of change of the volume of the sphere at that instant? Which formula would you use to start the problem? Not to finish the problem, to start the problem of these formulas. And we're talking about the volume of the sphere. 4/3 pi r cubed. 4/3 pi r cubed, exactly. This is a cone. What one would we start the problem with if we're looking at the volume of a cone? 1/3. Which one is that? D. Very good. It is D. Okay. Now we're going to actually solve a couple very basic related rate problems. Okay. Well, I wouldn't call this very basic, but of the more basic side. Okay. All right. So if we're solving this, we're solving it with respect to t, with respect to time. So what's the first derivative of the left side? 6x dx dt equals, what's the derivative of the right side? Ooh, you have to use the product rule. No. The first derivative, so it's x times the first derivative of y with respect to t plus y times the first derivative of x with respect to t. All right, now we start plugging in. We know dy dt is -3. We know x is -6. So it's 6 times -6. And I want to find dx dt. That's what I'm looking for. So -6 plus, I don't know what y is. Ooh, I need to figure out what y is. How will I figure out what y is?
Oh, you plug X into the original.
Oh, you're so smart. I love it, teaching smart kids. So 3 times -6 squared equals -6 times y. And then that's how I figure out y. So -6 squared is positive 36 times 3 is 108 equals -6y. If we divide by -6, I think y is negative 36, right? You agree? No. 18. I'm glad you didn't agree with me. There you go. Okay. So this is -36 dx dt equals positive 18 minus 18 dx dt. How do I solve this? Add dx dt. So -18 dx dt equals a positive 18. Divide by -18. dx dt equals -1. dx dt equals -1. All right. Okay, let's do another one. All right. How will we solve this? Well, I would go y to the negative first equals 8 minus x. So the first derivative of y to the negative first, -1y to the negative second dy dt equals, what's first derivative of 8? 0. So then it's -1 dx dt. Okay, plug in. So I have -1 times dy dt -0.5 over y squared, 0.2 squared, equals negative dx dt. So it's 0.5 divided by 0.4, which is 5/4. So dx dt equals -5/4. Okay? What if we throw in a trig in this one? How do we find the derivative of this? So it's the first derivative of sine is cosine of y dy dt equals negative 5 dx dt. We're solving for dx dt, so plug in. So the cosine of negative pi times 10 equals negative 5 dx dt. What's cosine of pi? 1. Or no, it's not 1. It's, no, negative 1. So it's negative 1 times 10 divided by negative 5. So dx dt equals 2. Okay? So, should I keep teaching and then just have the whole homework time after lunch, or should I stop? You do homework for a little